So let's take a look at the next hydrolysis, which is the hydrolysis of amides. So this can occur under acidic conditions, and it also can occur under basic conditions. So why don't we take this amide and let's react that with H3O+. So remember, H3O+ is what we're going to deal with here, but I'm going to write it out like that for the simple sake of reducing the number of Lewis structures that I have to draw. Now, often here we see heat being added. So we'll see that as a reaction condition, not all the time, but we often will. All right, now the very first step of this reaction is probably somewhat predictable as to what you've seen before. We're going to protonate or activate that carbonyl of our amide. That's going to form this with our NH2 here, just like so. And then I think at this point in your organic life, we can simply say here plus resonance, right? So we know that there's two other resonance structures here for this. So hydrolysis means we're putting water on there, right? We're gaining water. So the next step is water's going to come around here and grab that carbon right there. And then we're going to put a set of electrons from our pi bond onto our oxygen there. So that'll give us an OH with two lone pair. Up here we're going to have an NH2, and then down here we're going to have an O with two H's and a positive charge there. So what we're going to do next is we're going to do a little deprotonation. So we're going to grab one of these H's, so we'll use water to do this. So swing around and grab our H, give us this. Right, and now we're going to get our OH and your NH2s on position here. Right, now what's going to happen is we want to have this leave, but we're not going to kick off NH2 minus. Well, we can't do that anyway in a solution that's acidic. So what we're going to do next here is we're going to get an H plus from water. Now that's going to make NH3 plus, and then now that's a good leaving group. So we need to change that NH2. Right, what we want to do here is change this to an NH3 plus. That'll be a good leaving group. Right? So then over here we'll have our two OHs and then your NH3 plus. All right, now what's going to happen is we're going to have that NH3 plus leave. So we're going to swing around and do this. All right, so moving down here, that'll give us our NH3. Right, that's our leaving group. Then we'll have our benzene and an OH, oxygen, H, just like so. And then again, I think we've moved far along enough in OChem to just say plus resonance, right? So we have two other resonance structures there. Now the last step of this reaction is just the deprotonation to make our carboxylic acid. So we're going to add here H2O to do that. So we're going to take our water, swing around, grab that H, and then that will give us our carboxylic acid. So there's your carboxylic acid. And then also we have that NH3 that was eliminated too. Now the basic hydrolysis of amides follows a fairly straightforward mechanism. Now the mechanism that I'm going to show you now is from an advanced OChem book, and it's a little bit different than your textbook. So if you look in different textbooks, you'll find there are slight permutations on this mechanism. So I just want to show you the mechanism that I think kind of makes more sense. So we're going to start off here with our R group, carbon oxygen, and down here an NH, and then just to mix it up, I'm going to put an R group on here. So for the basic hydrolysis, we want to have hydroxide present here. And we will have an aqueous solution. Well, probably we're going to come over here and grab that carbon. Right, that'll make your R group connected to your carbon. And then we'll have an O minus up here. Okay, then up here we're going to have an OH. And down here we're going to have a nitrogen, and then I'm going to write this out as an NH like this. So we're coming over here next to our next step here, and we're still in a solution of aqueous hydroxide. So the question is, what happens next? Who gets deprotonated? So we could deprotonate here, or we could deprotonate right here. And these aren't solid numbers because they're slightly in different environments than a normal just alcohol or an amine, for example. But the pK of this comes from H2O, right? So if we look at the acid of that gives rise to this, that is a pKa of 15.7-ish. Now this guy comes from NH3, and that has a pKa of 36. So 15.7 versus 36. So in the presence of hydroxide, hydroxide is more likely to do a deprotonation up here on that top oxygen. So again, what forms here now is this oxygen with a minus charge and another oxygen with a minus charge, and then an NRH down here. All right, so here we get a dianion. And now what happens is these swing down to kick off our leaving group. Right, and then we're left with our carbonyl, a carboxylate, right, and our O minus, and then our NH minus. In the end, regardless of which mechanism you want to use here, whether or not it's your books versus this one is from March's Advanced OChem. But if you look at the next step here we just do an acid workup. In the end, we really get the same products. So that's going to give us a carboxylic acid plus NH2R. So the products are going to be the same here after you've done your acid workup.